Titration. Titration is the addition of a base to an acid or an acid to a base in the correct stoichiometric proportions, and every titration of an acid and a base will result in a salt and water. We're looking at Arrhenius acids and bases. So here's an example where I have hydrochloric acid plus sodium hydroxide, creating sodium chloride, which is the salt, and water. This is a familiar acid-base titration. So the question is, how many milliliters of a 3 molar solution of sodium hydroxide are required to titrate 80 milliliters of 4 molar solution of hydrochloric acid? So if I look at my balanced equation, and just like every stoichiometric problem, I have to look at my balanced equation. In my balanced equation, I require 1 mole of hydrochloric acid for every mole of sodium hydroxide. So if I'm looking at how many moles of hydrochloric acid I have or will need, then I have to multiply my volume times my molarity, right? My volume in liters times my molarity in moles per liter. Here's a trick though. If both volumes are in milliliters, you don't have to convert to liters. You can just keep them as milliliters because the proportion stays the same. So I can actually put it this way. I could say that the molarity, big M, times the volume of my acid will be equal to the molarity times the volume of my base, because it's a 1-to-1 ratio for my balanced equation, moles of acid to moles of base. Because again, molarity times volume equals moles. So 4 molar times 80 milliliters is equal to 3 molar times the volume of NaOH. And if I solve for that, I end up with 106.7 milliliters. So the concentration of sodium hydroxide is less than my concentration of hydrochloric acid. So it makes sense that in order to have the same number of moles of sodium hydroxide with hydrochloric acid, I'm going to require a larger volume of sodium hydroxide than I had of my hydrochloric acid. Now, what if the moles of acid don't equal the moles of base? So for example, if I have sulfuric acid, which is diprotic, and lithium hydroxide titrated, for this proper ratio in my balanced equation, I'm going to need 1 mole of acid for every 2 moles of base. My salt that I form is lithium sulfate, and I form water. This side doesn't really matter, right? So when we're talking about titration, it's really focused on the reactant side. How many do I have to do to make sure that I don't have a limiting reactant? So the question will be the same concentration and volume. So what volume of 3 molar solution of lithium hydroxide will be required to titrate 80 milliliters of sulfuric acid that has a concentration of 4 molar? So it's the same concentrations and volumes that we had in our last problem, but this time I have a diprotic acid. So because I need 2 moles of lithium hydroxide for every mole of my hydrochloric acid, it would make sense that I'm going to need twice the volume of my last problem. So this MV, molarity times volume of my acid, is going to be giving me 320 millimoles of my acid. I'm going to need 640, so twice the moles of lithium hydroxide. So I'm going to multiply this side by 2 because I need my moles of base have to be twice the moles of my acid. So 2 MV acid is equal to MV base. So if I plug in my numbers, I end up with 213.3 milliliters, which is in fact double the volume of the base that I needed in my last problem. When I look at a titration curve, this is what happens. So a titration curve is looking at the pH as more base is added. So it usually is an acid where I have a base, I'm adding a base. So what's happening is I first have an initial pH where it's just my acid alone, and then as I add more base to it, my pH will rise. Then I get to this point right here where my pH rises very rapidly as you near the titration point, which is also called the end point. So the titration point is going to be the point at which I add the amount of base that I need so that I reflect my proper stoichiometric proportions for my balanced equation. So basically, I don't have any limiting reactants at that point. The acids and bases are reacting completely so that I have no acid or base left over and I create nothing but my salt and water. So this portion, when you see this, you're getting very close to the titration point. And if you remember when you were doing your acid and base adding at the very beginning in your glassware, it got very close to here where your color would change, and you could see a color change that would, one more drop, cause the color to change really, really rapidly. That's reflected here in the fact that my pH changes. So my pH at the end point, when you see this curve, is halfway in this box. You can look at it geometrically, or you can look at it from a graphing point. This is an inflection point, right? So this is where my graph changes from a curve that's like this to a curve that's like this. So that's halfway up the steep curve. And the pH at the end point depends on the strength of the acid in the base. So oftentimes we think of it as 7, but that's not going to be true. That really depends on the acid and the base that I'm combining together. If I'm combining a strong acid and a strong base, HCl and sodium hydroxide are a classic example, they will dissociate completely. So when I am at my titration point where the moles of HCl equal the moles of sodium hydroxide, then what's going to happen is that the moles of hydrogen ions that are created through dissociation will equal the moles of hydroxide ion concentrations. And so I will have a 1-to-1 ratio, and that will be a pH of 7, right? I won't have an imbalance of hydrogen or hydroxide ions. pH of 7 at 25 degrees Celsius. If I have a strong acid with a weak base, so hydrochloric acid with silver hydroxide, the amount of hydrochloric acid that I put in will equal the concentration of hydrogen ions. But if I add a 1-to-1 ratio, so if I add the same number of moles of silver hydroxide, I will have not the same number of hydroxide ions. In fact, I will have less than that. So my moles of acid and my moles of base may be equal in my stoichiometric proportion. So I'm at titration. But what happens is that because I've dissociated my acid completely, but not my base completely, I will have more moles of hydrogen ions than I will have moles of hydroxide ions. So the concentration of hydrogen ions will be greater than my concentration of hydroxide ions because some of my hydroxide ions will still be stuck to the Ag+ ions as a definition of a weak base. So I will have more hydrogen ion concentration than I will have hydroxide ion concentration. That's a definition of an acidic solution. And so my pH will be less than 7 at 25 degrees Celsius. And finally, if you look at the last situation, I have a weak acid with a strong base. So hydrofluoric acid with sodium hydroxide. My sodium hydroxide dissociates completely. My hydrofluoric acid does not dissociate completely. And so as a result, even though my moles of hydrofluoric acid equal my moles of sodium hydroxide, some of those H+ ions aren't dissociating because they're still stuck as HF, and so my moles of hydrogen ions will be less than my moles of hydroxide ions. My concentration of hydrogen ions will be less than my concentration of hydroxide ions. Definition of a base, so my pH will be greater than 7 at 25 degrees Celsius.